Hi everyone, this is your sheltering in place virtual physical chemistry instructor, Dr. Hopkins. And so this video represents a start of our final unit or final part of this course, the physical chemistry course. And we're going to do molecules basically. And what I say is molecular structure. And what I mean is we've been doing molecules in terms of rotational and vibrational, but we're going to look at the electronic structure of molecules. And the electronic structure may be the most important part because that's the part that forms the bonding. That's what gives us the actual structure. It's what changes when we do reactivity. So it's one of the most important topics in all of chemistry. And so we're going to, in this first video, we're going to stick with the simplest possible molecule there is, and that is H2 plus. That's two hydrogens, so that's basically two protons and one electron, okay? And it turns out that that's it's the simplest molecule, and it's the only one that there's a possible analytical solution, because just like when we did the multi-electron atoms, once you had two electrons, because of the probabilistic nature and the wave-like behavior of electrons, you can't solve the problem analytically. So if we were to have just H2, we no longer can solve the problem. But in order to solve H2 plus analytically, we first have to make an assumption. And it turns out it's actually a pretty good assumption in that we have to decouple the motion of the nuclei, so the actual vibrational motion, from the electronic motion. Okay, so in other words, we're going to assume that the electron is moving so darn fast that it never really sees the nuclei move. It just sees stationary nuclei, so they're moving so fast. And that's basically the Born-Oppenheimer approximation. And the Born-Oppenheimer approximation is basically applied anytime you do any quantum calculations. Okay, so just about any quantum calculation is you treat electronic motion with fixed nuclei. Okay, if you do a vibrational analysis, you can move the nuclei, then solve the electronic part, move the nuclei again, solve the electronic part, and so forth. So it's broken down into pieces like that. All right, so let's set this up. So we're going to have the Born-Oppenheimer approximation. We've got a one electron problem, and we have two nuclei that are going to be fixed. So this is our Hamiltonian. The first part is our kinetic energy operator of the electron. I don't have it expanded out. We've seen that many, many times. And then the second part is our potential energy, which is based on the Coulombic interactions. Now, I don't include any centrifugal force to this as well, but there would be that term. But so this is just the electrostatic potential, and you have a 1 over r, that's the internuclear distance. That part's constant, okay? And then you have the 1 over Ra, 1 over Rb. So that's the distance from the electron to each of the nuclei. So now, rather than just one nucleus, there are two that the electron is interacting with or attracted to. And so in this case, our Schrodinger equation, H psi equals E psi, which we've solved over and over and over again, this actually can be solved analytically using confocal elliptical coordinates, which I don't really know what those are. I'd have to look them up myself. But it's actually not all that exciting because the only one we can solve that way is H2 plus, so it doesn't inform us any. It's actually much more interesting to solve this approximately. And we're going to do that using the linear combination of atomic orbitals to form molecular orbitals approach. So we're going to develop approximate wave functions, okay, or trio wave functions. You're going to use the variational method to solve those or minimize the expectation value shown at the bottom and figure out what is the best linear combination of atomic orbitals to make this particular molecular orbital. All right? And so in this case, for H2 plus, our two atomic orbitals are the 1s orbitals of the hydrogen atoms, so the two hydrogen atoms associated. And then we have these two variational coefficients, Ca and Cb, which are what are varied as you minimize this expectation value. All right. I do want to define some terms. So if we're doing the, if we're evaluating the Hamiltonian, the expectation value of the the hydrogen wave functions on one hydrogen atom, and where it's just one, it's phi A and phi A, which is on one hydrogen atom. So just solving the Hamiltonian on that atom, and then solving the Hamiltonian on the other atom. Those are what we are going to call Coulomb integrals. Okay, so this is going to apply across our entire discussion of homonuclear diatomic molecules. The Coulomb integrals are sometimes labeled as alpha. Okay, you could, if you want to think about them, they're the ionic character, right? So how much does each hydrogen atom want the electron to itself? And then on the second line, we have the cross term. So you have the 1s orbital on one hydrogen atom evaluated across the Hamiltonian of the 1s orbital on the other atom. Okay, and this is what we have both cross terms. This is what we call the resonance integral. Okay, and this is sometimes labeled as beta. And of course, now here is where we have this is not the ionic character. This is more of the covalent character of the bonding. And then there are also the terms on the denominator of our expectation value, because we don't know yet whether the overall wave function is normalized. So if you put the 1s orbital and 1s orbital on the same hydrogen atom, you evaluate that integral overall space, or the 1s orbital on the B hydrogen atom, evaluate overall space, you always get 1, because those are normalized. We've already shown that. And then the last term we want to set up or describe is the SAB term, and that's if you have, so now we're just going to evaluate the integral over all space for the 1s orbital on this hydrogen atom and the 1s orbital on the other hydrogen atom. Okay, and that's the orbital overlap integral, and basically that just represents like what is the extension of these orbitals into space. Are they close enough that they actually overlap in general? So those are some definitions that we use throughout this unit to keep in mind. But now if we'll go back and we're minimizing our expectation value, obviously you want to solve the first derivative or determine where the first derivative is 0 with respect to both of our coefficients, and the second coefficient should be CB. I have a typo here in this presentation. And that results in two equations with two unknowns, or simultaneous equations, and we're going to solve using a secular determinant. And here is the determinant. So the alpha, that's our, if we go back, that's our Coulomb integral, right, for the AA and BB. And now, since they're both 1s orbitals on hydrogen, we don't have to differentiate between the two. And then the beta are the cross terms between the 1s orbitals. So we have, here's our 2x2 secular determinant, which we would solve by doing the cross multiplication, and then you solve for alpha for your expectation values, and you should get two values. One is the plus, where we're adding the alpha plus beta, and the other one is the minus, where we are subtracting the beta from the alpha. Okay. Now I did want to point out that both alpha and beta are negative. Okay, so in other words, they represent attractive interactions. They're interactions between a positively charged nucleus, and actually two positively charged nuclei and a negatively charged electron. So those represent kind of attractive interactions. All right. And then our solution wave functions are the plus and minus for the corresponding expectation value are the overlap, or the addition of the two 1s orbitals or the subtraction of the two 1s orbitals. And then I ask a question here. So given these wave functions, what would you do to determine the coefficient in this case, so the CA? And actually I want to go back because I had a typo in the last slide. In this case, this is not a typo. The coefficient should be the same. And if you think about it, both nuclei are exactly the same. So both are hydrogen. So there's no reason that there should be more electron density on one of the hydrogens than the other. So Ca equals Cb, or in the minus case, Ca equals minus Cb. Okay, but then the question still remains: how would we use these two wave functions, or how would we determine the value of Ca for each of those wave functions? And we'll talk about that at one of our meetings. Okay, so our result, I showed the expectation value. Now I'm plotting it over the internuclear distance. So if we were to actually take the snapshot and evaluate what those two expectation values look like of those orbitals, the plus gives you basically something like a Morse potential, right? So it's a binding potential. If the electron's in one of the lowest states, it's happy it's there. You have to go out to long R's in order to get dissociation, so you'd have to really, really pull on it. But if we excite it into this E minus, as soon as you excite it into it, it just asymptotically goes out to dissociation. Okay, so one of these represents like a bonding orbital, and the other one is an antibonding, or it destabilizes the molecule. So you have one that stabilizes the formation of H2 plus, and one that destabilizes the formation. And so the pictures of these, and these really should be in brackets. So this is psi star psi of the plus. So the probability is that probability function. What it is basically both of our 1s orbitals, same sign or same shading, however you want to represent them. And you can see we have overlap between the two 1s orbitals. So once again, a bonding type orbital where there's electron density between the two nuclei. And then I did want to say a little bit about kind of labeling. This orbital type right here is what we call even parity. So in other words, if we were to invert everything, does the sign change? Okay, so does the shading change? And in this case, it does not. And so those are Gerada, or even parity orbitals. And then the bottom one shows the destabilizing, or the antibonding orbital, the psi minus probability. And you can see there is no overlap between the two. The overlap, or the electron density, is on the two separate atoms, right? So anti-bonding. And this is an odd parity. So if we were to actually invert these two sides, we would have the dark side on the other side and the light side on the other side, and we're changing the shading, or changing the sign of the orbital upon inversion. And those are Ungerada orbitals. Okay, so that is the kind of basis for LCA-MO in terms of H2+. That's for a 1 electron molecule. It's a pretty boring molecule. We're going to move forward with the same approach in the next few videos on more interesting homonuclear diatomic molecules. Until next time.